Hi everyone. Today I want to talk about another lock-in amplifier, the EG&G Power 124A, and this one is again a fairly old model from the 60s or 70s. I think it was built up to the 80s maybe. And these are the features over here. It's got a lot of features which are not found in some of the more modern analog or even digital lock-in amplifiers. So the range is typical in the high audio frequency to like the hundreds of kilohertz. So this one goes from 2 hertz to 210 kilohertz. It's got sensitivity on the input from 21 full scale ranges in a 125 sequence, and it's got a bunch of filters on the input side, which is again rare to see on a modern lock-in amplifier. Typically they come with a low pass filter, but this one's got flat, band pass, notch, low pass and high pass filter. And it's got some dynamic range controls where you can look at different types of signals, where if you don't want it overload, you can use different settings like a low drift, which has got the smallest dynamic range. There's a normal mode and there's a high dynamic range mode. And the manual for this particular lock-in actually goes into a lot of detail about how to use these different features, the analog features, also the noise features, and it's got a bunch of graphs and curves which show a lot of detail which I haven't seen in typical lock-in amplifier manuals. So it's very interesting to read through that. I'm not going to go into some of the details of this because I haven't actually spent much time on that myself, and it's fairly complicated and technical. So unless you're doing some very measurements that require that kind of level of understanding, you wouldn't probably look at that. But I think at some point I would like to go through that and study that part of the manual. So the other features are that it's got a calibrator which actually sends out a precise analog level. It's in a square wave type output into 50 ohms, and that is again it's got a fairly wide range of outputs, which is almost equivalent to the input range. So you can actually check every range for its calibration. It's got a Q control, which is interesting on the basically right at the input side, where you can select the filter, like if you have any other filter, you can actually select the Q of that filter, which is very interesting. It's got a time constant selection, which is typical in most lock-in to suppress, and to basically to look at the frequency. If you have a very low frequency, you want to have a certain time constant to reject noise and so on. So the time constant is very important, and it's got a good control on that as well. And it's also got a zero suppression, where you can remove a large part of the signal which is constant, so you can bring your signal down to the zero and get rid of some DC offsets using that particular feature. And it's got, of course, a phase control. So you've got a single meter, so you've got to use a phase control to look at either the in-phase signal or the quadrature, and you can have the four outputs, which are the 0, 90, 180, 270, and also you have a fine control on that, where you can actually shift that by a fraction of a degree. We'll show that in a measurement. Got a built-in PLL, of course, that locks into the input clock that comes in here on the reference. And besides that, you can, as you can see over here, you have the output clock, which is a sine wave over here on this synchronized driver output. And then you have a calibrator, which I talked about, which has a square wave output. Again, this is programmable. This one has got like 10 different amplitude levels, which you can use. Then as far as this is the clocking side, which I show in black, and then of course you can select the different filters here. The different dynamic range options over here, as well as there's an AC voltmeter mode where it completely disconnects from the reference clock, and it just measures a signal. So it doesn't do any frequency sensitive measurement. It's kind of more as far as the locking, as that is to find the phase frequency, like using a PSD type approach. It basically just acts like a voltmeter, and so that can be useful to determine the signal level without getting into the tracking of the frequency itself. As far as the signal path is concerned, you have the A and B inputs, which is one is positive, one is negative, so you can look at either one, or you can look at the difference with, using both. And the preamp, actually you can have different selectable preamps. You can remove them and plug in a different version, and they have different characteristics. So the one I have is the 116, which is fairly common. You also have the 118, which has a 10x gain built in. There are some other which have transformers and so on. So I haven't looked into those, but I do have the 116, which is I think a more general purpose preamp. There's an internal gain of 10, which is used then to actually determine overload levels, which can display once it's overloaded. You get a red light on the panel. And the amplifier itself has the mode selection, the frequency selections, and the Q selection, which is interesting. Normally, most lock-ins don't have a frequency and a Q selection. They just have a filter, which can be either high pass or with two different roll-off rates. But this one actually has multiple filters as well as multiple frequency and Q, which can tune the input side, the signal side, to a particular frequency, which helps with noise rejection. Then you have the intermediate amplifier, which then drives the synchronous detector or the phase sensitive detector. So when you do the lock-in mode, you are using the clock and the signal, and you're mixing them, and you're getting the output based on the frequency or the phase that's coming out of the VCO over here, and you can adjust that, of course. And so you can look at quadrature in phase or any other phase that you are interested in. And this, of course, here they have a time constant, and the zero suppression features are incorporated into this part of the circuit. And then you have the output amplifier, which then drives the detector output onto a BNC, or you drive the meter, and so the meter will display whatever the phase that you select over here, or if you're on the AC voltmeter, it will just measure the amplitude of the signal at a given frequency, more like a voltmeter. So that's pretty much covers this the block aspects of this lock-in amplifier. I would like to demo some features and then maybe also compare them with another lock-in amplifier which is more modern, and see how it compares in terms of performance and other things. Of course, it's an analog output, so it doesn't have the precise digital value like some of the Stanford research or the more modern EG&G or other types of lock-ins that are available from the 80s onwards. So let's look at that next. So here's the lock-in turned on, and it's got nothing connected to it right now. So starting with the reference section, which is shown in this blue, the box area over here, we have the frequency range control from 1x to 10x, 10kx, and then you have the actual individual digits. The decimal point is right here, and then you also can shift by 10 to get to the higher range, and using the red knob. And then you have the tens and the ones, and then this is the phase control, which has got a 10 turn type selection, where you can go down to like 0.2 degrees or so, and that's 0 to 100 degrees. And over here we have the coarse phase from 0, 190, 180 and 270. And here's the output, the sync output, which can be used to drive something else to give the frequency that you want based on this frequency setting here. And the level can be controlled, as I said, at 10 different values. There's a calibration thing which you can use the red knob to control precisely the amplitude. And of course you have the input clock coming in here, reference, and then you can also select the input or the external clock if you want to do external mode, where you can apply your own reference. And of course there's external divide by 2 or external divide by 1, so you can use twice the frequency as well. And then as far as the inputs are signal side, you have this area over here, which is the first preamp, which is a pluggable one, which you can remove using this knob. You can turn this, pull it out, and replace it with another version. Like I mentioned, we have the different 116 through 119. This is the 116, and you can have the A minus B, or the B, as well as You can select the transformer or direct, and then you have the signal channel, amp sensitivity, which you select 21 ranges from half a volt RMS to 100 nanovolts. Doesn't go as low as some of the more modern ones, but it's pretty good for that era. Then you have the frequency selection, just like the one for the reference channel. You can select the frequency of the signal, so you can actually precisely filter out noise and other things that may interfere or overload your lock-in. Again, you have the same 10x, the coarse frequency selection from x1 to 10x. And then here's the filter selection. You have a band pass, then you have the flat and the low notch, low pass and high pass. Then you have Q selection from, I think it's 1 to 100, and then there's a 10% of equivalent noise bandwidth selection. That's fairly, yeah, you don't see this in any other lock-in, I believe. This is pretty interesting feature. Not sure how useful it is, but I think you can get some different types of sensitivity selection based on this frequency selection, that you can filter out certain things with a sharper or narrower Q. And of course that is also controlled, the response of the whole instrument is also controlled by the time constant. So I guess they may be somewhat equivalent, but one is dealing with different parameters here. One is the time parameter, here you're dealing with selectivity parameters, so it's a little bit different I guess. And so here's the zero offset control, which you can use this multi-turn pot to control that, positive or negative offsets. And you also have a 10x multiplication on that full scale range that you can do over here. And then this part over here is the meter. Of course, the standard the meter used in many lock-ins and boxcar integrators of that time. It's a very nice meter. It's used in, as I mentioned, it's also in the other lock-in, the HR8 and so on. So here's the calibrator portion. We have also the selection, mode selection, which is the AC voltmeter mode here, where it disregards the frequency input and just looks at the signal. Then you have the off, and then you have the low drift, the normal and the high dynamic range for the phase sensitive detection. You have signal monitor, which can observe the signal coming out of the signal paths. And here's the output with the phase PSD output, which is the output of the, after you basically multiply the input with the clock, and that output and the DC output comes out over here, or DC or whatever the time varying component of that output at the given phase. And then you have the calibrator output over here, which can basically drive the input. If you want to see you can apply it over here and then get more accurate calibration of the input channel itself, or any other instrument that you want to calibrate. You can use this square wave output to do that. And here's the power switch, and there are a few things at the back. I won't go into those, but and there are some minor tweaks you can do here, like the notch adjustment and so on. But overall, these are knobs. It's fairly comprehensive, as you can see. A lot of knobs to play with, a lot of adjustments. So it takes a little bit of understanding to use this effectively, but I think it's a nice instrument to have, and we'll compare this maybe with one of the other lock-ins that I have. So let's look at some measurement now and show you some features of this lock-in amplifier. So here's my setup, a simple setup using two speakers actually. One is acting as a transmitter, as a loudspeaker, the other one acting as a microphone. Of course, the speaker is a very poor microphone, so anyway, since the lock-in can actually detect very, very small AC signals, it doesn't matter. I can easily detect it on this instrument above. And for reference, the instrument below is actually a boxcar integrator from the similar era of that time, in the 70s or 60s and 70s. You can see the similarity in how it looks, the meter, the knobs, overall dimensions and everything. So same chassis, I believe, but it's quite remarkable that they use very similar stuff, create a totally different instrument. But returning to this particular setup, you can see that I'll be applying a signal using the sync output from the lock-in, which is right here, which I described earlier, the reference going into the speaker, and then the input from the microphone will go into the one of the inputs of the preamplifier. And we also have a scale over here, which can probably help us to determine the speed of sound, I guess, based on what we know about the distance where the phase reverses, the phase completely goes through one 360-degree rotation. So anyway, the main thing is to see how this behaves with respect to interfering signals and so on. That's just more interesting as far as lock-in amplifier application is concerned. So let me set it up and then come back to the measurement. Okay, so you can probably hear a tone here. This is actually coming out at 3 kilohertz from the reference clock generator, and that's driving the speaker. And then on the input side, I have the same the signal being received by the microphone, and the frequency set at 2.98 kilohertz. It's slightly off because I think there's some drift or some offset in the frequency between these two, receiver and the reference clock generator inside. I could make it 3, but it will just be a slightly different amplitude, so I don't think it makes too much of a difference, but I just try to maximize the output for this given sensitivity, which is at right now at 10 microvolt sensitivity. You can see it's got the phase is set at 0, so that's the 0 phase output. It's got a negative value, and one thing you can try is to move to look at the quadrature. You move it to 90 degrees, and that's a quadrature level coming out. It's basically on a 10 microvolt scale. This is 4 microvolts, whereas the 0 was at minus 4.3 or something like that microvolts. And then you can look at the 180 degrees, which is plus 4.3 microvolts, and the 270 is at minus 4 microvolts. So I think, being a sine wave, it looks very symmetric around these 4 points. There's not much distortion in the signal basically that's coming in. So one thing I would like to do now is to show you the effect of the Q. There will be some amplitude changes as the Q is reduced. It actually spreads the signal over. It picks up some more. It not as selective, and actually reduces the amplitude coming out of the input stage. Whereas as I sharpen the Q, you get a much better signal. The other thing is the time constant. So in this particular case, it's probably no change because right now there is no interfering signal, and it's going to basically integrate that out and come to this final value, which is at minus 4 point or close to minus 4.5 microvolt roughly for this particular setting here. So one thing we can now try is to apply interfering signal and see how that we can see if the effect of the Q or the time constant can help you get rid of that interfering signal. Okay, I'm not sure if you can hear the second tone, which is very close to this particular frequency that is being generated by the lock-in at 3 kilohertz. I put in another frequency at 2.98 kilohertz from another source. My phone has got a function generator, and you can see that's actually beating with this external clock signal or external signal from this speaker, and they are mixing and producing this rapid movement which is corresponding to the frequency difference. If I go much too far different in frequency, it will probably not be able to respond, but this is close enough that you can actually see it responding. So one thing we can try is to see the Q effect here, whether that actually changes anything. You can see it doesn't really do much, except it widens the spread as we saw without the interfering signal, but it still has the same amount of deviation as far as the interfering signal is concerned. So the Q actually helps to reject noise coming on the input side, but really doesn't help remove the interfering part of the signal much. And because the time constant is fairly short, only 10 milliseconds, is actually being able to respond to that frequency difference, and doesn't integrate out to something that should be completely rejected if the lock-in was actually tuned to a much larger time constant. So let's increase the time constant so it starts to filter out the interfering noise, and now with a 1 second or even a 300 millisecond time constant, you can see that it's very stable, and I can prove to you that that the interfering signal is not creating any signal by removing the signal to the speaker, which is being driven by the lock-in, and see what happens to the output. So when I remove the output, you can see that the input has gone to 0, whereas you still hear the sound coming from the interfering signal, which is at very close to that same frequency, but it's not able to lock to that frequency. So the lock-in actually is very phase sensitive to the phase and frequency sensitive to the signal that is being measured, and so you can actually completely reject any interfering signals, whether they are close in or whether they're far away. It doesn't really matter. If over the correct time constant, you can integrate that out to 0. As you can see, if I bring the time constant down, it will actually respond to it, because it's actually at some point it's actually finding some signal level at a very high short time constant where the frequency actually contributes some signal to the measurement itself. So the best way to reject noise is to know your frequency response of the incoming signal, and whether the interfering signal can be removed by adjusting the time constant or the sensitivity on the time domain to basically cancel out to integrate that out to 0, the interfering signal. So now you can see the signals come back to what it should be, with the lock-in connected, with the speaker connected to the lock-in amplifier. It's now back to the same DC level we saw earlier. If I turn off the interfering signal, you see there's basically no change in the output, meaning that this particular setup is insensitive to any interfering signal within this frequency range we are talking about. So now let's look at one more thing. Now we have set this at 0 phase, and what I can try and do is to move the setup so you can see the phase moving as I move the distance between the speaker and the receiver, the speaker and the microphone. So currently we have a distance of exactly 500 millimeters, or half a meter. And as I move this up and down, you can see the signal will change in amplitude, and also the phase will move. You can see as I'm moving it closer, it's actually going in the other direction, and then it will come back and then return to the other side once I go through one whole cycle of the audio frequency for this particular frequency. So using the frequency information and the distance that I traversed to get one exact to return to the same point in phase will allow you to calculate the speed of the signal, or the wave that is being sent, the audio wave. So let's go back to the 600. So this is at 600. So exactly, half a meter. And the signal looks to be around 4.8 microvolts negative, and I'm going to move it all the way to the other side and bring it back to the same 4.8. I take the difference So 4.8 is roughly here. So that is 380 millimeters. So we have a 120 millimeter difference between the two points of the same phase in the waveform. From this we can calculate the speed of sound to some approximation. So here's a setup with a more advanced lock-in amplifier, completely digital with DSP. And what I've done is I've set the microphone and the speaker exactly the same as before, half a meter apart. And right now I've zeroed the phase, so it's close to 0 degrees over here. So it should be around 0, but it's just drifting around plus or minus a degree or 2. But that's good enough for this. The amplitude of the signal is about 8 microvolts for half a volt of RMS coming out of this lock-in at 300 at the same frequency of 3 kilohertz, which I use for the other lock-in amplifier for the 124A. So now what I'm going to do is to show you the effect of the phase movement again, to see if I can measure the speed of sound more accurately if possible with this, because of the resolution in the phase. Let's see how that goes. I'm going to slowly move it in, and then I'll stop when I get to around something like similar to around 0 degrees plus or minus a few degrees. So right now it's around -3. I could try and zero it out once more. So it's going down, as you can see. The time constant is quite long, so this is going to take a longer time to settle, 2 seconds. So it's about 1 degree or so. So let's now move this thing slowly inward. I moved it 30 centimeters, and you can see the phase is now changed quite a bit. I'm going to keep moving it in. So right now it's about on 180 degrees or so, minus 180. So it's about halfway there. And this is about 3/4 of the way from what I think it should be. So it's now gone to minus 70 or so. And now I'm going to be approaching the null again, or 0 point again. It's minus 30, 25, 20, 15, minus 8. Okay, we are very close now, so I'm just going to move it a fraction of a few millimeters and see what happens. Minus 11, minus 13. Because this time constant is very long, it does take a while to settle. 2 seconds would mean at least 5 to 10 seconds to really converge the phase. Could momentarily reduce the time constant to quickly acquire it, and then I can slow it down a bit. Okay, I think we are pretty close there. Maybe I overshot that a bit. Okay, let's assume it's around here, about 8 degrees or so. So back to the 2 second time constant. We are now at 483 millimeters, so that means 117 or so millimeters is the distance I should be calculating the speed of sound with. 483, 600 minus 483, that's 117. Okay, so I did the calculation, and at 20 degrees Celsius the speed of sound is approximately 343 meters per second. I'm seeing from my calculations 350 51 meters per second, or 785 miles per hour. The actual measurement is at 20 is supposed to be around 767 miles per hour. So we are very close to the actual value based on this measurement. So basically, using a more accurate digital setup, I'm able to get more accurate. But I think the 124A was pretty good. I could probably improve that measurement if I did it more carefully. But I think this illustrates that point. So another thing is, of course, the interference part of it. I think because this lock-in is got probably a better resolution on the phase, as well as on to be able to higher Q on the using a digital approach. It might be able to reject close-in frequencies better than the other one. Let's see. I'm going to put in a tone at 2.995 kilohertz, which is just 50 hertz away from the actual frequency I have here. So let's try that and see what we get. So we'll see how that does. I have a very short time constant, and I expect quite a bit of interference because at some point it will be lining up with the peaks will line up and the troughs will line up, so we'll get some interference, and as I increase the time constant, you'll see that it will actually filter out the interfering signal much better. So let's turn on the interfering source now. You can see that the signal is around 9.8 microvolts, phase is 0, and 20 millisecond time constant right now. So let's turn on the source. Now you can see that there's significant amplitude modulation. The frequency, the phase also is moving around quite a bit, and that's because of the time constant again being very short, and it's not able to filter out the interfering sound very well. So increase the time constant, like the other one, where I'm going to go to a longer time constant, and you can see it's starting to get much better. The filtering is much better at this point, and as I increase this further to around half a second, you can see that it's probably completely gone, completely filtered out. And this is the beauty of a lock-in amplifier. It's just extremely narrow band, high Q operation in removing signals buried in noise, and so that's one of the applications. You can see clearly here that it's doing its job. So essentially the time constant is one of the important things, even though the Q doesn't play that much of a role. As you can see in the previous measurement, the same thing happened. The Q didn't have much of a role to play when time constant really cut down on the interfering signals. So you're back to no more the signal off now, and you can see the phase is pretty much at 0. So here we are at the end of this video. Sorry it was quite long and I didn't actually get to some of the features like the calibrator and some other things in this 124A, but I think basically we covered the description and the functional block diagram and features of the EG&G Power 124A lock-in amplifier. I demoed the interference rejection abilities using 2 different sounds and a simple speed of sound measurement. These you have seen before on other YouTube channels, I'm sure. But anyway, this is just to demo this instrument. Then I compared the instrument with a more modern signal recovery 7280 DSP based lock-in amplifier for the same experiments we did for the 124A. As far as I could tell, given the simple measurements, both lock-ins did a very good job on these experiments to be able to reject interfering sounds, as well as to do some measurements using the phase abilities. Didn't really test the limits of either of these lock-ins, but you can see that the sensitivity and resolution of the modern lock-ins are much higher, along with more advanced analog and digital post-processing abilities. Again, we didn't get into any of that. The key difference, I think, the 124A produces an amplitude at a given phase determined by the reference clock phase that you select on the front panel. whereas the 7280 actually gives you the amplitude and phase with respect to 0 phase when you first turn it on and don't do anything with it, and then you can actually makes it easier to find the phase of the signal of an input signal even if the signal amplitude changes, which is because you have the phase information which is independent of the amplitude information. And then the 7280 also allows you to zero out that phase, which can be useful to measure the phase differences along the waveform and giving you x and y or r theta values simultaneously. The 124A, you can do the same thing, but it requires you to tune the signal, the phase input, the coarse and fine, as well as you have to know where to look for the signal. So that's a little bit more cumbersome, but it can be done. Other differences are that the newer instrument only has a low pass filter which actually has 6 dB or 12 dB roll off, which you can enable if you want to. It has got a notch ability, or sorry, a band pass ability, whereas the 124A has more analog controls for filtering the Q and as well as the type of filter you want to do. Perhaps these features were deemed unnecessary in the more modern lock-ins, and so they resorted to more advanced post-processing features which allow you to do more difficult measurements with signals that are buried in noise and so on. But at the end of the day, I think the modern amplifiers are simpler to use in some way, getting rid of some of the analog features. So hope this long video was useful to demo the 124A and compare with a more modern lock-in amplifier. See you next time. Thank you.